Say an AI learned something dangerous, how to help build a bioweapon, and you want it truly gone. There's a whole field for this, called unlearning. But here's the dirty secret. Today's unlearning doesn't really work. A few minutes of fine-tuning can bring the dangerous skill right back. This paper has a surprisingly simple fix. Let's name the problem precisely. Current unlearning methods don't remove a capability, they just suppress it. The model stops using the bad skill on the surface, but the knowledge is still sitting there in its weights, dormant. So an attacker can simply fine-tune for a few steps, a relearning attack, and wake it back up. The authors run a clean thought experiment first. Imagine the perfect unlearned model, an oracle that was never trained on the bad data at all. Now take a normal model and train it to copy that oracle's outputs exactly, perfect behavioral agreement. Surely that's truly unlearned. And here's the unsettling result. Even with perfect behavioral agreement, identical outputs, the copied model relearns the forbidden skill far faster than the real oracle does. Matching what a model says on the surface is not the same as changing what it secretly can do. The capability is still latent in the weights. So what actually works? The paper's beautiful core finding. Take that suppressed model and use it as a teacher to train a brand new, randomly initialized student from scratch on the teacher's outputs. Good behavior transfers to the student, but the latent, dangerous capability gets left behind. There was never any hidden skill in the fresh network to begin with. This single figure tells the whole story. On the left, the reference model, full of dangerous capabilities, shown as little red devils. Unlearning grays them out, suppressed but still lurking. Then distillation pours the behavior into a fresh network, and the devils are simply gone. They had nowhere to hide. Why does this work? Because the hidden skill lives in the specific arrangement of the teacher's weights. When you distill into a fresh, randomly initialized network, you only copy the visible behavior, not that weight structure. The student has no latent capability to relearn, so it resists attacks about as well as the perfect oracle. There's a catch, of course. Training a whole new model from scratch is expensive. The gold standard alternative, retraining on perfectly filtered data, is even worse. You'd have to label every single training document. So the authors ask, can we buy robustness more cheaply, dialing the cost up or down as needed? Their answer is a method called undo, unlearn, noise, distill on outputs. Instead of a fully fresh student, you take the suppressed model and damage it, adding noise to its weights, partway toward random. Then you distill the behavior back in to repair it. The more you damage first, the more the latent skill is destroyed. And that gives you a dial. Add just a little noise, and you get cheap, mild robustness. Add a lot, and you approach a fully fresh network, maximum robustness, but more compute to repair it. One knob smoothly trades compute for how truly forgotten the capability becomes. Here's that trade-off in action. On the left, robustness climbs almost linearly as you spend more compute, tracing the gold standard frontier. On the right, the relearning curves. The unlearn-only model in pink collapses instantly under attack. Undo in blue stays flat and robust, hugging the gold standard in orange. And the headline numbers are striking. At its strongest, undo matches the robustness of that gold standard retrained from scratch, while using only 60 to 80% of the compute and needing only about 0.01% of the data to be labeled. Nearly the best possible result at a fraction of the price. Does it hold up beyond toy tasks? A test on WMDP, a benchmark of proxy weapons of mass destruction knowledge, bio and cyber, using a real GEMMA model. Across 7 different adversarial attack scenarios, adding undo consistently made the unlearning more resistant to relearning. The effect is real, not just an artifact of synthetic data. And here's the practical kicker. Distillation is already standard practice. Frontier labs routinely distill big models into smaller ones to cut inference costs. So if you just run unlearning before that distillation step you're already doing, you get robust capability removal almost for free. So the big idea. There's a gap between what a model does and what it could do, and ordinary unlearning only touches the first. Distillation into a fresh network discards the hidden capability while keeping the good behavior. It turns a routine efficiency trick into a genuine tool for making AI forget, for real. That's Distillation Robustifies Unlearning, a clever way to make AI truly forget. If this helped, subscribe and tell me which paper to decode next.